0 after robbing a bank in Dodge City. Sounds like a good old Western, doesn't it? I like Westerns. My favorite one would be 310 to Yuma. It's a great movie. The robber gallops off. The robber doesn't gallop off. The horse gallops off. It's just the robber is on the horse. I didn't think I had to explain the robber was on the horse, okay? So robber gallops off on his horse at a speed of 14 miles per hour. 10 minutes later, the marshal got notified and leaves in hot pursuit at a speed of 16 miles per hour. How long does it take the marshal to catch up with the bank robber? Do you agree that the marshal will catch the bank robber at some point? Yeah, it might be an hour later, it might be a day later, it might be 10 days later, but eventually he's going to catch up, right? It's going to happen. So what do you think? Is this a situation? Obviously, we know this is a distance, rate, and time problem. But what is the same? Is their rate the same? Is the time the same? Or is the distance the same? Talk to the person next to you. See if you can decide in 20 seconds. What is the same of those three variables? Talk. Go.
The rate is the distance and the time. The distance is going to be the same because I'm going to each
different spots.
So yeah, but the distance from that spot is still going to be the same. The distance will be the same, we just don't know it, you know?
Because
when
they both
the time is
yeah,
right? Usually you have 10 minutes.
I just think because when they both
The
go
rate
to
is
the
obviously
point,
14 versus 16.
Okay, what is the same?
In that,
Is their rate the same?
you're not going to square.
No.
Absolutely not. Is the time at which they're traveling the same? No, the one is traveling 10 minutes longer than the other, right? Their distance is the same. They eventually overtake one another. That means that they have traveled the same distance. So we are going to say that the robber distance is equal to the marshal distance. I think I misspelled marshal in the problem. I think it's 2 L's, isn't it? This is an English class, Mr. Gens. And I do know that distance is equal to rate times time. Rate times time. Well, this works out well for me because I know the marshal's rate. What is the marshal's rate?
16.
16 times time. Sweet. What's the robber's rate?
14 times.
14t. Subtract 14t, we get 0 is equal to 2t, t is equal to 0, right? Done. Ah, we're missing something, aren't we? What are we missing?
The robber is 14 minus 10. 14t minus 10.
Like he gets a head start. Like time represents the time that the marshal is traveling, right? Like we didn't account for the 10 minutes at which the robber got the head start, right? So what distance does the robber cover in his head start? Distance is equal to rate, which is 14 times time, which is 1/6 of an hour. 10 minutes is 1/6 of an hour. Yes, no? So as Brecken said, 14 over 6 or 7/3. That's the distance he covers. Plus 14t is equal to 16t. Now we have a real equation that will give us a solution. 7 over 3 is equal to 2t. Divide both sides by 2 or multiply by 1/2. If you multiply by 1/2, you get 7 over 6 is equal to t, which is 1 1/6, or 1 hour and 10 minutes. 1 hour and 10 minutes. What do you think of that, Abby Lynn?
I wouldn't have come up with that on my own. That's interesting.
But now you've seen it. So now you probably could. But you want to get to the point where you can come up with one on your own, right? And that's your challenge with problem 14. Can you do it? Can you do it? Can you do it? Okay? We expose you, and try to have you try something on your own. The next one, this is our last problem for this section of 1.6. I love this problem. Does anybody remember the Pep Fest the other day? I was in it. How was I dressed? Like a winter guy. Who's I walking with? Luther. What was he carrying?
Kayak.
A kayak. I had offered him a different prop. I had offered him an umbrella, and he did not take it from me. And lo and behold, here in this situation, we come across a problem with a beach umbrella. And what did I just happen to have in the classroom today? I happen to have a beach umbrella. Somebody said that that was bad luck to do that inside. I don't believe in luck, folks. Last hour said that if I did this during class, I would run the risk of Ben stealing it and using it as a weapon against other people in class. Is that possible?
I would never.
You would never. Interesting. I said, who is most likely to cause destruction with that? And they said, Ben or Big Bird. So, all right. Just never going to get old, dude. All right, here we go. We're on a boardwalk. Love boardwalk. Boardwalks involve water, right? It means we're at the beach. We're having a good time. We're at the beach. We're having a good time. There's an umbrella. The umbrella's sitting like way over here. What's a boardwalk? Don't say a weary walk that's made out of boards. Tell me something more. Why do they have boardwalks? What do they do? Make it so you don't have to walk on the sand, because sand is hard on your knees, right? Stuff like that, right? So yeah, so there's a dude over here. He's got a really long neck. Okay, he's on the boardwalk. He's walking. His umbrella's over there. If there's water and there's a boardwalk, there's probably a shark out in the water somewhere. We all know that. There's probably somebody swimming for their life. Kind of add a little bit there. Kind of add some interest to the problem. Okay. I was in the ocean a couple of years ago. Took my family to South Carolina, and I yelled shark. I did. I was like, everybody needs to get out of the water. Okay. There was big fins. They were coming right after people, but they were dolphins. How am I supposed to know? People started laughing at me. Like, what? Like, it looks like a shark, a big shark that could do some serious damage. Give me a break. Here's what we know about it. We know that the man is exactly 750 feet away from his umbrella. We also know that this umbrella, this beach area, it sits 210 feet from the boardwalk. Now, he walks at a certain speed on the boardwalk. On the boardwalk, he walks at 4 feet per second. On the sand, he walks at 2 feet per second. Does it make sense that he's slower on the sand? So the question is, if he's to walk on this and at some point veer off, at what point should he veer off such that he makes it to his umbrella in exactly 4 minutes and 45 seconds? Everybody agree that, like, the dude's he's not going to take time to figure that out, right? You guys are like, okay, there's no application here at all. But there is. I could give you many instances. I'll just give you one. We're not smart enough to tackle this problem yet. We have to get to next week before we tackle it. But here's a different situation, okay? Lifeguard is on the shore. Lifeguard sees a distressed swimmer. How far does the lifeguard run across the land before he enters the water and then swims towards the distressed swimmer so that he reaches the distressed swimmer in the minimal amount of time? That's a good question, right? Now you guys are like, why would a lifeguard do that? Lifeguards don't do that, but mathematicians sit down and they figure that out, and they tell you, hey, if the guy is way out there, then this is approximately the spot you run to. If he's close to the shore, then this is the spot you run to. They give you general ideas, and they use mathematics to figure that out. So we want to figure this out. This is a distance, rate, time problem. And it's a time problem because we have to end up with a specific amount of time, 4 minutes and 45 seconds. So right away, my mind is drawn to this idea that distance is equal to rate times time. And if I solve for time, I have distance divided by rate is equal to time. That's the equation that I want. Because if I say the time on the boardwalk plus the time on the sand, that has to be equal to 4 minutes and 45 seconds. Again, I come up with a basic idea to represent our equation. Now, his speed is in feet per second. Feet per second. So can everybody be okay with the idea we need to change this problem to seconds? So 4 minutes, that's 240 seconds, plus 45, I got 285 on that deal. 285. This is time on the boardwalk, time on the sand. Time is distance divided by rate. I don't know the distance on the boardwalk, but I do know the rate. What's the rate on the boardwalk? 4. Plus, I don't know the time on, or the distance on the sand, but I know the time on, or the rate on the sand. It is 2. That's got to equal 285. So I've got both my rates, got my total time. Now I just need my distances. Just need my distances. Let's look up there, see if we can figure something out. Anybody see something we can figure out?
The distance for the boardwalk.
Yeah, so Ben sees that the distance here to here, we can figure it out using the old Pythagorean theorem, can't we? Right? We got x squared plus 210 squared is equal to 750 squared. I need some help with the calculator today. We got some big numbers we're going to be working with. So I go to my handy dandy calculator, I take 750 squared. And I'm going to subtract 210 squared. And is that my answer? I got to square root that guy. Square root the answer. And I get 720. So that means that this total distance in blue is 720. Now I'm going to put something in place here that's going to help you out as you encounter a different problem eventually. I'm going to say that this distance right here is x. If this distance right here is x, who can tell me what this distance is?
720 minus x.
Very good. 720 minus x. So therefore, the distance on the boardwalk is 720 minus x. Now, some of you may recognize that you could have put the x here and the 720 minus x there. You could do that, but then this piece gets messy because now I want to find this distance right here. That's our distance on the sand, isn't it? And I can use the Pythagorean theorem as well. The distance squared is equal to x squared plus 210 squared. I can do a right triangle Pythagorean theorem right there as well. And if we square root both sides, we get the square root of x squared plus 210 squared. And that is that distance. So, square root x squared plus 210 squared. As a mathematician, I'm absolutely elated at this point because I see that I have an equation. It has one variable. And as long as I've got one variable, it is easy to solve. Sir?
Why can't you just cancel out the squares and square?
Yeah, let's do that. Like the square root of, let's try that, guys, sometimes. Square root of 25 minus 16, right? What's 25 minus 16? 9, and you square root, you get 3. But if you were just square root that, you'd be like, oh, well, it's 5 minus 4 is 1, right? You can't distribute powers over addition and subtraction. It just doesn't work. If it was multiplication, you can do it, okay? Good?
Yeah.
Did he just stare you down? Yeah. He might be upset about the phone number. Okay.
That's phone number.
Oh, all right. So here we go. I don't like the fractions. Anybody else don't want the fractions? How do we get rid of the fractions in the equation? Multiply through by? What do you multiply through by? So with an F rhymes with or. Thank you, 4. Multiply through by 4, I get 720 minus x. Notice that the 4 divided by the 2 gives me a 2. And I get 4 times 285.
1,060.
1,140.
Yeah.
It's all right. What do you want to do now? I mean, if I've got a square root, everybody going to have to agree you're going to have to square both sides at some point. Do you want to square both sides right now? No. What do you want to do first? Yeah, let's get rid of that 720. You get negative x plus 2 roots of x squared plus 210 squared is equal to 420. I don't want to square the left side with that negative x over there, so I'm going to move that x over to the other side, and I get 2 roots of x squared plus 210 squared is equal to 420 plus x. A lot of people want to divide by 2 at this point, and that is an option. However, I would encourage you to square things at this point in order to avoid having a fraction in your problem. As I square this, I square 2 to get 4. As I square the square root, it goes away. I'm left with x squared plus 210 squared. And now I'm going to square this. I get x squared. What are you going to get in the middle?
840x.
840x. And they get 420 squared. Well, it's time. We've got a second degree equation, which we're happy about because we just gather everything on one side. We either factor to use a quadratic formula, but we're going to have to take some of these big numbers here and kind of expose them. So let's figure out what it is. I've got 4x squared plus, somebody give me 4 times 210 squared.
840 squared. Wait, no. Got squared first.
Got squared first. 176,000? 400? I got x squared plus 840x plus, and what is 420 squared?
Pretty big number.
176,100.
Ooh! I have 176,400 in both situations. So those could just, I could just subtract that off from each side, right? They'd be gone. Gather my other like terms. I gather an x squared over. I got 3x squared. Subtract the 840x. That equals 0. What do you want to do now? Should we factor out a 3x?
Yeah.
I take a 3x out of 3x squared, I'm left with x. And 840 divided by 3, 280. So therefore you have solutions of 0 and 280. Now let us look back at the problem and see if that answers the question. X is 0 and 280. So x is 0 and x is 280. So the question is, how far should he walk along this boardwalk before he veers off? Well, it's whatever 720 minus x is. And if you do 720 minus 0, it would be 720 feet is how far he should walk. Or 720 minus 280, which is 440 feet. He's got two options in order to get there exactly in 4 minutes and 45 seconds. It's a little bit of a problem, isn't it? Think it's possible that anybody could ever do one like this on their own? Like any student? Like, let's say it came up as an extra credit problem on a test. Think we could have any student who get that right?
Is that foreshadowing?
You're smarter than you think you are, folks. People have had many successes with these problems. And so, for you, look at your homework, and I'll show you where you can head right now. I told you yesterday to work through problem, what, 18?
Yes.
Now you can carry yourself through problem 21. 22 is optional. You do not need to do it. Although, challenge extended, 22 is a problem that very, very few people who I've encountered in this class are able to figure out on their own. It is reserved for the best of the best. If you are the best, try to figure it out. Go. I'd love to see your work. Okay? Problem 21 is very similar to what we have just diagrammed, but I'm going to put the picture up for you, okay? So if you would like to write the picture that goes with 21, here it is. Instead of a person, it involves a bird. The bird flies over the ocean. It's not as fast over the ocean due to the wind that comes off the water. It is faster on land, and you'll find that in the rates. It actually burns a certain number of calories. The island that it flies from sits 5 miles off the shore, and then from the shore it's an additional 12 miles over to the nest. The bird flies to a certain spot and then heads over from there. Believe it or not, birds actually have an innate ability built in them to know how to fly over different areas with currents so as to conserve their energy and optimize their production. It is amazing how they're able to do it. They're able to pick a spot. There you have it. That's the picture. You guys have the rest of the hour, which is a solid 15 minutes. I'd love to help you on any questions that you have. But since you are an extremely intelligent class, maybe you have all the problems already figured out. Goodbye, YouTube. No special word today. Should we put a word in there for Viv?
Yeah.
Sophie, what's the word?
I don't know.
The word is
Bedbugs.
snuffleupagus.
That was Diego that recommended.
Yeah, it's from what?
By the way.
Oh.
Bug beds.
It's
From Sesame Street, right?
Yeah.
I was thinking of Big Bird, so how about snuffleupagus? Snuffleupagus. There we go. You get the word.